¿No viste a Elsa, una bajita?
No,
No.
no. Antes.
¿Va a dar ponencia ahorita?
Sí.
¿Trae equipo?
No.
Nomás lo voy a platicar.
No trae mi mismo. Dijeron que aquí va a estar un equipo.
Ok, estos equipos son de transmisión. Con lo que usted vaya a preguntar, no sé. Le puedo conectar el equipo que traiga para que proyecte, pero busque quién le va a proporcionar el equipo.
Porque yo leí que iba a haber equipo para...
Vaya con quien le dijo que va a haber equipo para que le proporcione el equipo.
Ok.
Sí, creo que es mi noche. Ajá. Es para invitar, ¿no?
Aquí están los, bueno, este es su paquete,
Ok.
su reconocimiento y también el de todas las presentaciones de cada una de las presentaciones.
Sí, presentación de ahorita, ¿no?
Ajá, sí, de ahorita.
Ok. De mis alumnos para mi Cara y Francisco.
Ajá.
Tienen que estar aquí, ¿no? Para con el equipo.
Sí, había una chica que trae
Bien. Ok, sí, ¿sabes? Sí.
para que lo apoye entonces.
Sí, sí, gracias.
Sí, ahorita
Sí.
le doy el apuntador.
Ok, muy bien, gracias. Entonces no tenemos el computadora, ¿no?
No,
¿No?
estos no son para...
Sí, sí, pero para la presentación de usted tiene.
Me dijeron que buscara rápido.
Camisa cara. Ok, esperamos. Ok.
¿Qué tal, Luis?
Bueno, sí.
¿No tiene computadora aquí? Ah,
Olvídalo. No, esto es para transmisión de la inauguración y de algunos plenarios. Entra en computadora con quien les dijo y esa persona ya me autoriza a dejar por adicional. A ver, voy con tu visita.
Doctor, buen día.
Sí.
Francisco Jurado, mucho gusto.
Mucho gusto.
¿Cómo está?
Bien, bien.
Qué bueno, qué bueno. Pues aquí estamos ya listos, igual. ¿Falta computadora?
Sí, me presenta todo bien. Para la invitación.
Vaya. Bueno, pues ya, se va poniendo todo a tono. Siempre sigue el valor del 85 y tú igual 102. Ah, es que sí, es cierto, son menos de valor positivo ahí. Más rápido. No, aquí no me funciona.
Sí, no sé qué tenga que estar haciendo.
No, sí. Empieza a funcionar, no vale.
It's done now, so for this section I have used English and but still I think it's a good to try. So you can start now and 50 minutes.
15 minutes? Okay. Good morning, everybody. Here my topic is about an optimal contact force of robots in unknown environments using reinforcement learning and model-free controllers. First, let's consider the following control problem. We have a robot manipulator that has contact with an environment. This environment is modeled as a spring damper system where KE is the stiffness and CE is the damping of the environment. Here, FE is the contact force that occurs when the robot has contact with the environment. Here, this model can be modeled like this model, where this XE is the position of the environment. When the position of the robot is greater than the position of the environment, there exists the contact force. So, since we are in discrete time, we discretize this model as the following form, where A and B are given by these expressions. Then we want to design an optimal contact force between the robot and the environment when this environment is unknown. First, let's consider that the environment is known. So we have the following scheme, where the inner loop is a position controller and the outer loop is a force controller. Here the inner loop is a model base such that the robot dynamics that is given by this equation has a feedback linearization by using this model-based control, where this U is a PD control, such that this is the inner loop has desired dynamics and follows a desired trajectory given by the inverse kinematics. So the force controller uses as input an impedance model which is designed using the environment parameters. So when we know the environment parameters, we can design an impedance model such that its output is a desired force that can minimize the position error between our reference and using this desired force. So what is the main problem of this approach? That we require the knowledge of all the robot dynamics and the parameters of the environment, which is not always available. So our approach proposed to use reinforcement learning to learn directly the impedance model. Since the impedance model has as output the desired force, then reinforcement learning learns the optimal impedance model and the optimal desired force. Also, in the inner loop, we have the same control, but instead of using a model base, we use a PID control with model free. And instead of using the inverse kinematics, it is designed in tag space, since the desired force gives as output a position reference in the Cartesian space or tag space. So we have the force control is designed as a PI force control, designed as this form. So let's first consider how we can design the impedance model when we know the environment parameters, which is a linear quadratic regulator case. So we want to design an optimal desired force of the following form. That's a feedback control using a stabilizing gain L, which minimizes the following discounted cost function. Here, S and R are the weight functions from the tracking error and the desired force that is our input. Is our input of the impedance model. Then the solution of this problem can be obtained by using a discrete algebraic Riccati equation that is given on the following form, and the stabilizing gain is given by this expression, where P is some kernel matrix that is designed according to the parameter A and B. Here is the problem: we need the knowledge of the parameter B and A. So we can, if we don't have knowledge of the environment with this controller, and we need to use another kind of methods like estimation or identification methods. So in our approach using reinforcement learning, let's define the following Bellman equation. That is the same cost function, discounted cost function, written as an iterative way. R is a reward function that we want to minimize in this case. So if we use the Bellman optimality principle, we have a desired force is given by the arc mean of the optimal Bellman equation. And since this optimal Bellman equation can be written in form about the tracking error, we have that this expression can be written as a Hamiltonian matrix given by this expression. If we take the partial derivative with respect to the desired force, we obtain the same optimal desired force. But here we don't have knowledge of the environment dynamics. So we can write this function as a co-value function using an iterative way. So here we don't have knowledge of any, we can compute an optimal desired force using only measures of the tracking error and the desired force input. So how we can compute this problem is by using reformal learning, and one of the most famous approaches are using Q-learning and SARSA. This Q-learning and SARSA, you store all the combinations of the tracking error and desired force in lookup tables, so such that in every iteration, by using this update rule, we can obtain the optimal Q function that minimizes the reward function. So the only success of these algorithms is that we have to explore the whole space of the combinations of the tracking error and the desired force. And here, this Q-learning is known as an off-policy control method, and SARSA as an on-policy, because here the policy learn is not using the minimal co-function in this part. This is the target function. And in SARSA, we use the control policy to update the com function. So the problem of this is that we require a long time of learning time. So we can accelerate by using LGBT traces. The LGBT traces is a long short-term memory that assign credit of the visit states that we already have visit, and is given where this lambda is the trace decay factor. Then in the update rules of Q-learning SARSA that are given is for SARSA Q-learning, and the rule is modified using the LGBT traces as follows. Then we test with our approach by using a parenting robot, a 6 degrees of freedom force torque sensor, and an environment with stiffness and damping. It's a steel box with non-stiffness and damping. And here the environment is located at 0.5 meters, and the reference is given by these expressions. We can see that the reference is greater than the position of the environment. Then we have a contact. We compare all the methods that I mentioned, that is Q-learning, SARSA, Q-lambda, and SARSA lambda, with the model-based linear quadratic regulator to show how reformal learning can calculate the optimal desired force without knowing the environment, and we use model-free controllers. First, since we don't have knowledge of the environment dynamics, we have to use recursive least squares algorithm to estimate both damping and stiffness, which convert to the following values. So with these values, we can compute optimal desired force using the linear quadratic regulator problem. Then we have the following results by giving these gains for the PI control, which is K as 50 and 10. Notice we don't have derivative gain since the robot presents high. And the force control use the following gains. These gains are chosen such that the robot, when it touches the environment, keep at the environment location and not penetrate the environment. So we have the following results. Here the first one is the desired force, and we can see that all methods convert to the same value, but with different transient response. We can see that reformal learning learn the optimal desired force in a better way than the linear quadratic regulator. Here the linear quadratic regulator penetrates some and give a big value of the force so that the environment can be damaged. And here the reformal learning give a little penetration and then stabilize to the optimal desired force. Here is the tracking performance of our reference. Here line is the desired reference, and the yellow one is the location of the environment. As we can see, first the linear quadratic regulator penetrates the environment and then stabilize at the environment position. Meanwhile, the other ones only penetrate a little bit and then stabilize. The other one, here is the learning time of our algorithms, where we can see that could last. Each algorithm learns in 1,200 episodes as 1,000 steps, and we can see that other reformer learning methods stabilize at more or less like 200 steps to obtain the optimal desired force. And in conclusions, we propose a simplified model-free robot interaction control using reformer learning, and we only learn the optimal desired force, and we don't require the model parameters, and instead we use a force torque sensor to measure directly the contact force. We use a PI force control to generate the new reference tracking, and the PID to guarantee position tracking. And we give some experimental results using a 2 degree of freedom panel tilt robot using a 6 degree of freedom torque sensor. And we make the comparison between the LQR and reformer learning, and we show that our reformer learning methods can learn the optimal desired force without knowing any of the environment dynamics and using model-free controllers. And that's all.
Okay, so here is we have a 7 minutes for question and comment.
I have one.
Yeah, okay. Yeah.
Okay, why are you using a linearizer model?
In the right model?
Why? We have the reason to use a linearizer model for the robot. I assume that the robot can move in a very large task space. So, is your linear model still valid?
I don't have a linear model for the robot. We have a linear model for the environment. The environment is modeled like a spring damper system, and it's the only one that is modeled like a linear system.
Okay.
The robot is still not linear.
So if this linear mode, you can identify the model. Accuracy would be better than this one now.
Yes, the advantage of reformer is that we don't need any model. So
Yeah.
we only need measures of the input of that in this model is the velocity and the position, and we only require that measures and the measures of the contact force to obtain for this kind of system. And if we want a nonlinear system, is given we require some other methods to.
Yeah, information, comment. Okay, thank you. This one. Here.
Who's next?
Okay. So our next speaker is Jorge. He will explain how to use neural network to learn human behavior. Okay. Right.
Hello everyone, thank you all for being here. I'm presenting human behavior learning in joint space using dynamic time warping and neural networks. First of all, I want to start giving you an introduction, and then I will start talking about human behavior, demonstration processing, and learning using neural networks, and how all of this is applied into a specific case of study. After all, currently the robots are controlled manually, and if they're not, they're prone to follow a specific path, which is pre-designed. But in specific applications like in exoskeletons and surgical robots, robots allowing to perform tasks and skills in a similar way to a human. But in order to this robot be able to generate these movements, first the robot needs to learn these movements. So the learning process can only be done in the workspace or in the joint space. If the learning process is done in the workspace, we will need the inverse space. We will also have problems of speed and precision. In this current work presented today, we're only focusing on, by the speed problem in the joint space, I mean that let's suppose that we want to teach the robot the specific task of 8 in the workspace. So in order to increase the generality of we use 2 demonstrations. These 2 demonstrations have the same trajectory, or almost the same trajectory, in the workspace, because they are at different speeds, so we need to align them. The human behavior learning is based on the learning by demonstration. This is a technique. Actions and states are first stored and then learned by the robot. They are carried out employing a subject, which is called a master, teacher, and the robot who learns the demonstrations is called. And the human behavior learning has been divided into 2 phases: behavior learning and behavior generation. As I mentioned before, the main problem is to align the 2 different demonstrations at different speed in the joint space. So we use the dynamic time warping to align them. And this algorithm starts from the individual alignment of each joint X, demonstration number 1 and demonstration number 2. Then we create a matrix where the Euclidean distance defines in this way, and then we define a warping path denoted by this, where the first element of the warping path will always be, and the next elements will be like this. So the easier way to find the elements in the warp A and B is by finding the minimum element in the matrix previously defined in matrix. So once we find the warping path, we will have individual warping paths, and if we do the direct kinematics of these warping paths, we will see alteration in the trajectory in the workspace. So in order to avoid these alterations, we need to apply a global warping path for the whole set of joint signals. To obtain this global path, we do an average alignment warping path, and we obtain it based on the shortest individual warping path. We obtain that warping path following this average, and then we obtain the average warping path, and then we can apply it to the whole set of joint signals. Now let's suppose that if we choose A and B in such a way that they form a warping path for a joint signal X corresponding to demonstration number 1 match in the same trajectory in the workspace, another joint signal X would correspond to demonstration at different velocity in the same trajectory. We can signal like this, we define a sampling data step, define it as this. So the sampling that step, we will obtain this and applying it to the. Okay, now the learning using neural networks, we propose feed-forward neural net, a single hidden layer, because this architecture with at least kappa number of hidden neuron allows with almost linear activation function learn exactly kappa different observations. So the relationship between the input signal and the synaptic rates is denoted by this expression, where A and X is the synaptic rates matrix vector X, where we include the dynamic memory P, and the vector V is denoted by the hyperbolic tangent activation function, and the output layer with phi number of outputs. The output layer is this. P and Q, all the synaptic rates matrix of the family, and the second matrix V is obtained by minimizing the approximation error in the sense of error, following this expression, and the optimal solution for this expression is given by this, where dagger is the generalized inverse of Moore-Penrose of the matrix previously described B. This. So the output layer will be this. And now for the experimental, so we apply all of these algorithms in a 7 degree of freedom robot. And we obtain demonstrations from the robot, a demonstration number 1 and a demonstration number 2 at different speeds. So using the dynamic time warping algorithm described to keep the frequencies below 3.5 Hz and attenuate the higher frequencies. So once the filter is applied, we obtain these outputs where in comparison to the trajectory, we see that we eliminate the noise in the workspace trajectory. Now applying the change of velocity, we see that if we apply change of velocity times 20 and 30 and 40 times, we start seeing here that we have alterations in the trajectory in the workspace, while we see in the times 10 no bigger alterations in the trajectory in the workspace. The conclusion at work is that the method improves in speed and precision the human performance in tasks thought through demonstrations, and since it has been done in the joint space, the inverse kinematic has been no need. And also, the learning can be severely affected according to the complexity of the task to be learned. The more complex the task is, the higher the number of neurons are needed. For the future work, we will increase the size as well as cover a three-dimensional workspace, study the primitive movements, and explore operative capabilities in dynamic environments. All of these using deep reinforcement learning. This is all. Thank you all for your attention.
Thank you. So we have almost 10 minutes for question and discussion. Comment. Yeah. Okay. Yeah.
Do you only use the same? Is the same demonstration for all your experiments? And only is different the velocity. It's the same. For example, it's a sine wave of amplitude 1 for all experiments for different velocity or different frequency.
You mean? I think I'm not understanding. You mean if I use the same demonstration for the experiment?
Yeah, the same demonstration for different velocity.
Yeah.
Okay.
The thing is that has the same trajectory in the workspace, but at the moment of to generate these demonstrations, I don't know. I think like I want to do an 8 slow, and then I want to do it fast. It's almost the same trajectory in the workspace, but they have different velocities in the joint space.
In future work, you mentioned that you want to, for example, you want to make a line, or for example, you have a big net and small lake. This is your proposal for future work? When you have different size of egg, because they are different, they are the same egg, but they don't have the.
Also, one of the things we want to do. Also, we want to cover not only a plane, it's not a three-dimensional space. So I don't know, like making an 8 in a not in a plane, if not a, I don't know, like move or rotate over 1x.
The conclusion is no. Until now, you can do this one in the space. But I mean, if you use your train with 8, you can generate 8 also. But it cannot generate 0. No, it's
Only
not safe. Or safe is impossible. No, it's a difficult task. I mean, I think more complex neural network maybe reinforcement learning. Oh no, deep learning. But now, no, it's possible. Yeah, good.
Well, I'm surprised by the large number of neurons you need. 700?
Yeah, 700.
Okay, have you explored or are you thinking maybe to explore the use of recurrent neural networks or dynamic neural networks? Because I guess using this kind of networks, the number of neurons will be reduced.
Yeah, well, the thing, we use this architecture because it was easier to train using extreme learning machine, because extreme learning machine only works for one hidden layer. So we use this, but yeah, afterwards we will explore recurrent neural networks.
Okay, and my other question is, the learning is done online or offline? Online. How easy, because you know, when the robot is really doing the task, maybe there will be an external disturbance. Are you thinking on that? I don't know, maybe a kind of problem on the trajectory.
Yes. Well, the architecture, it's here. It has a not closed loop. So yeah, we probably will have problems at the time of executing the states in the robot. But yeah, in the future, I think we will include a closed loop. I think with a camera in order to follow the specific path.
Yeah.
Well, can you tackle the dead zone? Or the backlash to the trailers for the robot, because your trajectory description is very good and it degrades as it reaches more velocity. But maybe I think that the precision of in the description trajectory maybe it's so good if you tackle with the backlash from the trailers of the robot.
Well,
maybe as the Dr. Sanchez commented about maybe the disturbances or imprecise movements of the robots when describing the human behavior learning.
You mean how could I control the backlash?
How can you tackle? Yeah.
Well, actually, the robot has the backlash. Here it's a little backlash in one of the joints. So I think we could control it through a closed loop in using.
Earthquake, but it's shorter. Earthquake is impossible to predict, but it's shorter. Okay.
Okay, thanks. Good morning. The next topic is short-term prediction of the earthquake through neural networks and meta-learning. And content, the introduction, the multi-layer perceptron, meta-learning, transfer learning, conclusions, and reference. It's important that if you try to predict the earthquake, maybe you say that I'm crazy, no? But in these days in Mexico it's a currently topic because it happens 20 years ago, no? I think that the neural networks have, in this case I use feed-forward structure, and has some problems. For example, you depend of the training data, you depend of the initial weights, you depend of the method to learning process, and I think in machine learning exists several tools that it's possible to improve this structure. Yes, maybe it's a simple structure, but meta learning means that they take the control of the process learning and take the experience to improve the prediction. And the transfer learning is from the another task, how am I going to use this knowledge to improve the process learning of the main task in the earthquake. The normal method to train a feed-forward is a backpropagation, maybe with the term to momentum, and it's now how am I going to predict the next event using the past events. In this time, it's a project with the CNR in Italy and the Simbe, and in this place, using this is a complete new topic for me, but in this place, using not the date, not the place, not the hour of the and specific numbers. Take a characteristics, a features. For example, how much time to pass for the before event, how much distance for the before event, and how is the magnitude. And the problem here is how to use the knowledge of magnitude to predict maybe the interdistance event time. And that's interesting because we have the next. This is the currently structure of the feed-forward. We have an input layer, one hidden layer, and the output layer. The input is the consecutive events before to the present, and the error is given by the equation 3, is the estimated output minus the real output. And the index to minimize the backpropagation is the mean square error. This is not important. All the people make this easy. But this is the real contribution or the real objective of this paper, the meta-learning. John Biggs described the meta-learning as being aware of the taking control of one's own learning, and it's taken from the psychology. And I think in some comments of the review of this paper, one referee say, okay, why you use old technique or simple technique? And I say, okay, maybe I probably gonna use deep learning, CNN, or another complex algorithm. But maybe in this place, a lot of people is an engineer, no? And I think that we need to find the simple way to solve the problems all the time. What happened? Maybe I'm gonna take a complex algorithm, but if I use a data of earthquake, that means nothing, because the probability that the event happens tomorrow with a specific place is meta-neural network. This meta-neural network is another MLP, but offline I'm going to take the inputs as several inputs and form to the universe S with the initial conditions of the weights and find by the index of ms, the mean square error, an optimal weights of the hidden layers or the layers. And after this, I'm going to propose a while condition to find the maximum angle between two vectors, the weights of the initial and the optimal weights, and find the vector xk with the same dimension of the weights of the hidden layer or the input layer or the output layer. And you can find hat eta. This term is possible to add to the backpropagation law and have to the convergence, or maybe, for example, if you propose any initial conditions on the weights with low data, it's possible that you found a minimum local. And with this, I'm going to help this neural network to avoid this neural network to minimum local and improve his learning. And for example, we have the no, but with the meta learning, it's better. But the problem, it's the same. How I'm gonna say a good prediction of our earthquake, even I have these results? So how I'm gonna take these results for the numerical part and the real characteristics? So the earthquake, how I'm gonna prove that this happened, no? And this is a comparison of the mean square error. The blue is MLP and the red is E plus meta learning, and it's better practically all the time. But if, for example, if I try to predict the sale of petroleum tomorrow using the sale of petroleum today, it's easy. But what happens if I avoid the first consecutive 3 data in the training and the testing? The MLP is worse, but the MLP plus meta learning, it's better, because it's clear, because the backpropagation depends on this, the optimal weights in the hidden layers and the input and the output layer. And this is the mean square error. All the time, the meta learning, it's better. Now, what's mean transfer learning? Transfer learning is you have 3 main. The first task, maybe it's to predict the petroleum. The second task is predict the change of dollar. And the third task is maybe predict the temperature of the day. The domain is different between the second task and the third task. But the domain in the first task and the second task is similar. The problem now is how I'm gonna use the knowledge, the task 1 and the task 2, to improve another task. And that's mean transfer learning in a simple terms. But we have 3 issues with transfer learning. Okay, we have 3 tasks, but what going to transfer? This knowledge is maybe the pattern of the if you see the behavior of the task and you see the some pattern, maybe I use this part only to take this knowledge and improve the main task. But the problem now is when I'm going to transfer. Yes, maybe, because not all the time the behavior of the task is similar. And maybe in some point of this stage, we have to form a negative transfer. The problem is how I'm gonna write the law when it's possible to transfer the learning or not transfer learning. And the final issue is how to transfer. And this is many ways to transfer learning. All the ways the behavior is optimal, or maybe a optimizes approach. But now, how I'm gonna use the transfer learning in this problem? The first task is the magnitude, and the second task is inter-event time. I use 10 data set for training in the second task. It's impossible to make a prediction with this small data set, but I use the final weights of the first task in the initial conditions of the second task. And I found this. This is MLP plus the transfer learning. And the inputs avoided the 3 consecutive events before the present. And it's better. Yes, of course, it's impossible to have or maybe a 0 in error, but it's better, and you have the MSE prediction. And finally, I think that it's a simple to show how the meta-learning and transfer learning helps to improve another task. And I have these conclusions. The big problems of the neural network model is the selection of the learning parameters. And that is true, because all the time it's a proof and error, and several times. But this paper is another way to help or to make a prediction with a simple feed-forward neural network. And I think that it's interesting because my area of research is automatic control, but I tried to other areas. And I think that I can use this problem to improve the predictive control, because this technique to control is to predict the next step and anticipate it, the control that you use to force the input to follow another reference. No? And this method increases the speed of convergence and gives greater the flexibility of the parameters of learning. It's like an auto-synth of the initial conditions on the weights in the neural network. Some reference of this, like that. Thanks.
Thank you. Question?
Well, I think that you need to give us your assumptions that you account to
Okay, yes.
areas, because as you know, the earthquakes.
It's a complex task.
Yeah.
In
the
the
center is located at different locations.
Yes, for example, I visit Italy. In this place, his name is Potenza, and Potenza is a mountain. And I think that in the mountain, the earthquake it's effects in the city. But no, 15 years ago, earthquake destroys Potenza, and I say, okay, it not depends of only of one feature, depends of many things, no?
Yeah.
And for example, in this case, one hidden layer, And the hidden layer I use 6 neurons. The output for it's 4 because I use 4 consecutive before, and only 1 input. Output. And the main objective of this paper is to show that it's possible to improve a simple task.
Yeah.
No?
Yeah, I understand that, but I think that the assumptions
Sí,
are
yes.
important. And you know, every earthquake has its movements, trapezoidal,
Exactly.
trapezoidal, directions, temporal space data.
Yes. The problem is the catalog is only say this is the catalog and you make it. No, maybe I need to find these features and.
And why use data from here or from Mexico?
It's a project with the Simvestab and the CNN, and they here for that.
Well, thank you.
Yes.
This transfer learning is new. Is your
No,
proposal, or are you
It's regularly
taking from another works?
the transfer. It's taken for another works,
Okay.
but in this increase the use this approach is in machine learning. It's high in this moment.
So the conclusion is short term. So how long? It means from one event to another event. It's like replica, like 1 day, 2 day, or
Okay. It's
how long can?
It's an inter-event time, maybe 1 month, 1 week. For example, the training data in this moment is 4 months consecutive before January, and it's a short time to make a prediction because the last month to make a training is in December, and I use January 2007.
So you can predict earthquake 1 month later?
Yes,
Next
1
time?
month. It's not a date. It's an event.
Okay.
The next event. Maybe
Yeah, right.
maybe the next event
For 10
passes.
years after 10
See,
years.
maybe
Okay.
the probability that it
happen.
happen.
It means
See.
if you have earthquakes, then you can predict 1 month later. No?
Yes.
Yeah, like this. There's a problem because
See, it's
if you said you can predict the earthquake in Mexico City next year, okay?
no. Maybe I'm going to say
It's impossible. Impossible.
the 19th of September
Okay.
will happen, and maybe I'm going to the jail or something like that. No. For example, in one comment, the referee say, "Why you no make a prediction?" It's a risky way to say, tomorrow in the Mexico City happen a earthquake with a 10 in magnitude. No?
Or I think that almost you can define or establish what is the main goal to predict the magnitude of the next event, nor the date or.
See, no, it's a future of the next event.
Yeah.
No?
To prevent.
See, exactly. It's to prevent, and maybe in some places, and I say maybe it's possible happen someday. This happened with these characteristics. No, and maybe you prevent the people and save the lives. Maybe it's possible. No, it's interesting topic. No.
Yeah, very interesting.
I have a question about the experimental data. What are you measure? At time t, I measure magnitude or something? I don't understand.
No, it's, the Dr. Luciano gave me the events, only events, but the times, I don't know.
Okay, but this an experimental data is a time and magnitude of the earthquake, or
The
what
x-axis is the consecutive events, and the y-axis is the magnitude. normalize it, obviously.
Only this data.
And in the first task is magnitude, and the second task is an inter-event time. And use the knowledge of the magnitude to improve the process learning in the inter-event time.
Okay, thank you.
Thank you.
So we conclude this session. Great. Okay, great.
¿La suspendo? Ah, sí. Ah, tenemos.
¿Y cómo va lo del Congreso del SNC? ¿Siempre se va a hacer?
Vamos a ver, porque para mí no me gusta yo trabajo, pero le iba a hacer case. Case es congreso.
Sí.
¿Tú sabes? ICA. Sí, tú sabes el congreso de ICA. ICA es robotic.
Sí.
Other automation.
Sí,
entonces, case va a ir al típico 2022. Sí, todo acabado. Todo. Entonces, si quiere, porque vi eso como che. Yo digo, ok, bien. Mira, tú sabes, iba para comunicación. Ahora estoy buscando también más importante a la Ciudad de México y apoyar esas sociedades de México. Pero la mayoría de ellos son chinos. Son chinos. La mayoría no son. Robótica no, robótica. ICA es muy internacional, pero ¿qué es más chino y Estados Unidos? El chino y Estados Unidos.
Hace rato, no sé, que era el director de la unidad, se me encontró una vez en Puebla, me cayó la tarjeta. Sí, ya, bueno, ya está más tanto solo. Yo tengo mucho tiempo en la una vez ubiqué a Sergio Marcelino, ¿tú lo conociste?
Sí, claro. Tú lo que sabes.
Tengo su correo, lo debo tener ahí, pero no lo vi, lo ubiqué porque iba a dar una plática en UNAM y ya supe y sí nos contactamos y bueno, tal, pero no.
Lo que estoy intentando es compilar con yo.
Sí, como no, lo voy a ver.
Bueno, yo puedo saludar puertas aquí. 2, 3, probando.
Esta es la presentación. ¿Dónde la cargué?
¿Cuál presentación?
La
No sé nada de eso. Bueno, aquí está el laptop, iba yo a dejar ese tono, pero ¿lo van a operar? ¿En qué parte va a ser de la inauguración?
Aquí está bien, pues, para...
¿En qué parte de la secuencia de la...?
ok, no es una... O sea, es esta información,
sí.
la que está en la USB.
Ajá.
Para que tú nos ayudes a iniciar.
Lo iba a leer así directo,
así
pero...
como está.
Ajá.
Así como está, directamente, pero no, para que también se vea aquí. Para que se vea el programa en la pantalla. Y en algún momento cuando hablemos de la página para decir que ahí están la información.
Bueno, la página ya la dejo, ahí está cargada.
Sí. Pero digamos, si tú nos ayudas a dar la bienvenida y esta información, claro. lo general, o sea, lo que está más logrando esto, digamos.
Y luego presentó el presidio.
Sí, de hecho desde acá, desde aquí donde está la organización.
Sí.
Después el presidio va a estar José Luis Leiva, Wenyu, Sergio y yo.
Ok.
Y la presentación general. O sea, esto podemos hacerlo más ágil, ¿no? La presentación general con algunos tópicos dados por los chairmen.
Ok.
Y la ceremonia de inauguración, pues, la formal va a ser por el representante. Si no llega él, pues entonces no lo hacemos.
Ok, sí.
Sí, y por ejemplo, todas estas páginas va a hablar Wenyu, esto de los keynote speakers va a hablar.
A ver, ¿esto lo va a decir Wenyu?
Wenyu, sí. Pues entonces yo no. Pues va a ser Sergio Salazar, esto es Sergio Salazar. Y a partir de aquí voy yo. Y a partir de aquí voy yo.
Ah, usted va. Ok, correcto. Nada más presento y el aviso de seguridad.
Sí.
Entonces, déjame subir esto para acá.
Julio, ¿qué tal? Bueno, ya ya en la página, ¿verdad? Ujú. Está bien. Sí, para en cierto momento ya salgo y le doy a la página.
Su permiso para grabar, joven.
¿Su permiso?
Ah, también. Pues de las fotos de Sor Juana antes de que desaparezcan, 2 cada uno.
¿No de Sor Juana?
Sí. Antes que desaparezcan los de Sor Juana Inés, ¿qué billete traía Sor Juana?
Bueno, o sea, nomás espero sí que llegue. Digo, porque iba a llegar Ricardo Félix en la dirección, pero no llegó. Pues ya sabes que aquí improvisamos.
Sí.
Si quieres, al final, ya cuando terminemos, pues tú vas a hablar también de los arreglos, ¿no? Puntos para que se vayan conectando.
Sí, 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 sí.
Perfecto.
¿Está bien aquí? ¿No estorbo mucho?
No.
¿Me meto allá?
No, ahí estás bien. Ahí estás bien.
¿Lo están enviando a través de
YouTube, a nuestro canal.
¿Eh?
A nuestro canal.
Ah, sí, ya.
¿Ya qué? Lo tengo desde hace más de 10 años.
No digo, pero ahorita ya lo estás todo
Sí,
enviando.
todo, hasta ahorita aquí.
¿Y con qué están grabando?
También con el laptop. El laptop graba y transmite.
¿Y dónde lo pones? ¿Ahí? Digo, ¿la cámara? ¿Dónde está la cámara?
Está ahí, ¿dónde está?
Ah, esa.
Y la webcam de la laptop está viendo al público. Yo tengo otra cámara, está en la mesa viendo a los chicos.
No, pues yo no sé qué hago aquí, entonces yo me voy. Yo pensé que no estaba haciendo nada. Bueno. Pero no se te corta, no sé si se cae la red.
No me importa, se está grabando y ya después lo subiré.
Ah, sí, también lo estás grabando aquí.
Pues transmite simultáneamente.
¿Con qué software estás haciendo eso?
Con OBS.
OBS. ¿Es libre? Porque con pasa Uy, qué bien.
Mira, vino hablando de no, empieza por la parte en inglés y cuando termines, más información. Ya le dije,
Good morning, everyone. 16th International Conference on Electric Engineering, Computer Science, and Automatic Control 2019, and the opportunity to give a warm welcome to everyone, authors, attendees, colleagues, students, personnel, and visitors. Give you a heartfelt welcome to Simbastab at Mexico City, Mexico. We sincerely wish you a fruitful and enrichment. This year has been all past years. Now, as a legal requirement, I need to address you the civil protection announcement. Simbastab counts with 2 seismic alert systems. This building has 1 local alarm. An evacuation of the installation must be carried out with all the local alarm sounds. Everyone has to exit the auditorium in a manner orderly, not running, not shouting, and ahead of the group try to open the doors, open the way, open the path for everyone who's following you. Don't worry, don't worry to go back to pick anything in case of an emergency. In any case, the seismic alarm sounds or the local alarm sounds, we have to evacuate the building. No one must remain inside this. Ahora, para ofrecer esta ocasión, invito a Armando Navarro López, de Protección Civil aquí de Simbastab, para que nos dé las indicaciones pertinentes. Por favor, aquí el...
Con mucho gusto. Buenos días a todos. Como ya se explicó, en el centro contamos con 2 tipos distintos, uno para caso de sismo y otro para casos de incendio. En caso de que se activara el sistema de alertamiento sísmico, vamos a evacuar inmediatamente, vamos a salir por la puerta de acceso y vamos a situarnos justamente en el círculo verde que está en el área de estacionamiento. Evitemos entonces retrasar la salida con nuestras pertenencias o con cualquier otro objeto que pudiera llamar nuestra atención. La intención de esto es salir inmediatamente y ocupar el tiempo de alertamiento previo para el evento y sitio. Como información adicional, nos es muy importante que permanezcan en el punto de reunión, en el círculo verde, para que estemos identificables y el personal de Simbastab se aboque a hacer la revisión de las instalaciones post al evento para continuar con la actividad que llevamos hasta el supuesto evento sísmico. En caso de que haya un evento por cuestión de incendios, de la misma forma evacuaríamos inmediatamente hasta ese sitio y nos mantendríamos alertas para recibir instrucciones al respecto. Muchas gracias por su atención y buen día.
Thank you very much. Now, allow me please to present the people that is making company here. First hand, I want to welcome Dr. José Luis Leiva Montiel, Planning Secretary at Simbastab. Dr. Wen Yu Liu, Co-Chair at CCA 2019. Dr. Sergio Salazar Cruz, Co-Chair CCA 2019. Dr. Gerardo Silva Navarro, Co-Chair CCE 2019. And now to do a general presentation. Who's coming first? Dr. Wen. When you address you to the opening presentation of this event.
Okay. So, first welcome everybody, and I give a brief introduction of this conference. Let me see what is. Oh, here. So, this conference It's been in 1905, and at the beginning it's a national conference of this, the Department of Electrical Engineering, EE. And after 2004, and it became the imprint. And in fact, this conference now we have three parts or three departments. One is the Department of Electrical Engineering and Department of Automatic Control and UMI. You can see the three parts. So we have three co-chair for this conference, and this conference focuses on also these three parts. We call this electrical engineering, computer science, and automatic control. So you should pay more attention to your paper. We cannot accept. It means we need at least two reviewers. So not so. I mean, it's not so easy. 80%, and the paper comes from the almost a lot of countries, like Asian, like Europe, okay, main part is from Mexico, no? Latin America. You can see this. We had almost 11, 15 countries. Okay, so I think that common this conference from beginning or from originally we hope will give you a platform for young professor to present his recent result. So now we still focus this area. So I mean we also hope all students from Mexico or from Siemens or your friends from another place to in the future to submit your paper, because it's as you say, because we are supported by Siemens, so the registration fee is very, very low. It's only $300. Is almost, you can see. I think no any conference has this kind of low education. It means we give you a chance. I give you an opportunity to show your new result. Okay, thank you.
Now, to give you a deep overview about this, Dr. Sergio Salazar Cruz is about to address you on this matter. Welcome.
Thank you very much. Thank you very much. I would like to thank the CCA organization and the Professor Silva and Professor Wayne for the invitations. I talk about the plenary sessions. We have three. After this welcome, we have the first is about the data driver and computational control for certain nonlinear systems by the Professor Ki Wang. He's here. Professor is Professor and Chair at the Department of the Applied Mathematics, University of California, Santa Cruz, USA. After tomorrow, we have another plenary session, sliding mode controllers, stage of evolution, by the Professor Leonid Friedman, who works in the Department of Control Engineering in National University Autonomous of Mexico. And the Friday we have the last session, the last plenary session, is about the sliding mode control, a frequency domain approach by Professor Herbert Sierra Ramirez, I think is here, by the Department of Electrical Engineering of Sinvestat, Mexico. Thank you.
What will be of us if we don't remember those ones who were among us? And for speak for and remember and make a little memorial session, Dr. Gerardo Silva Navarro is going to address and remember those who were before us.
Okay. Thank you very much for your attention. Thank you for coming to this conference. And tomorrow afternoon we will have special 2 memorial sessions in honor and memory of our colleagues from the section of bioelectronics in the electrical engineering department, Professor Roberto Muñoz Guerrero, Professor David Elias Viñas, with some colleagues, students, and friends and family, just to remember our colleagues who passed away in several months ago. Okay, the conference we have different topics. This year we have most of the papers are concentrated on automatic control, but we also have on biomedical engineering, computer science, computer engineering, also communication systems, mechatronics, mechanical engineering, nanotechnology, materials and applications, and power electronics, solid state materials, electronic devices, and integrated circuits. Also, this time with the participation of the UMI LAFIA Simvestab CNRS, the autonomous navigations and exoskeleton. So there are some events part of the CCE 2019. First of all, I want to remember that the official language of the conference, because of the character as an international conference sponsored by the IEEE, we have to use and to speak, to give the talks in English. And I think this is a good training for our students and also for okay, as part of the CCE, we have coffee breaks, no alcohol permitted in Simvestab here at 6:30. And tomorrow, after the memorial sessions, we will have some ceremony, alcohol, but just to remember our colleagues, tomorrow afternoon we have this time that this is CCE in an eco-friendly fashion. That means that this time the proceedings and also the program is contained in our webpage. So the schedule it can be downloaded from the webpage, and also the proceedings. So the proceedings will be available during September. And after that, the proceedings, the papers, the technical papers, will be sent to the IEEE Explorer for the chairs, session chairs, authors, students, colleagues, for the valuable time and effort to continue this conference, inclusive during these years where we have financial problems. Okay, so this conference is celebrated with the valuable help and support by Simvestab, the General Direction, the IEEE sponsorship, the IEEE Electron Devices Society, the International Program Committee, our colleagues, our co-chairs, Professor Wen Yu, Professor Sergio Salazar, and myself, personal students, and we want to acknowledge and finally thank you for coming, and we hope that you enjoyed of the conference and also to continue after this year the series of the CCE's conference. Thank you very much.
Now to formally do the opening of the ceremony, I invite Dr. Montiel to address you words for this opening.
Welcome. Let me change to Spanish because I think the information, the ideas I want to share with you is about our situation in this moment. Entonces, permítame, with your permission, I will change the encryption. Desde el inicio del año hemos estado en una posición que nunca habíamos pensado que íbamos a estar, ¿verdad? Nos han movido completamente el panorama y yo creo que por un lado eso es bueno, porque hemos empezado de alguna forma a reflexionar acerca de va haciendo la ciencia correcta o no. Principalmente hay dos motivos que provocan esto. Uno es la nueva dirección del CONACYT y la otra es el cambio de ley de ciencia y tecnología. Está cocinándose ahorita en el Senado de la República y que si ustedes ven la nueva propuesta que hace el Senado, similar a la que tenemos vigente, simplemente que hay un cambio muy drástico y es que se le da todo el poder al CONACYT, les quita el poder a los otros órganos que de alguna manera regulaban o regulan actualmente políticas de ciencia y tecnología en el país. Y eso es de alguna manera grave, ¿verdad? Porque hay órganos que son muy importantes, el Consejo General de Ciencias, que está formado por los secretarios de Estado, por los presidentes de consejos de ciencia y tecnología de los estados, que son muy importantes escucharlos. Está formado por algunas instituciones, los directores, rectores, como el CINVESTAB, la UNAM, Politécnico, que deben de participar, y este órgano tan vital apareciendo. También está desapareciendo la Conferencia Nacional, que es el órgano formado por todos los consejos y secretarías de ciencia y tecnología que tenemos en el país y en la Ciudad de México. Y eso es, por un lado, de alguna manera, las prioridades que tienen los estados sobre su desarrollo económico, científico y tecnológico y humanos, y lo estamos haciendo a un lado. También se está quitando el Consejo de Ciencias, el Consejo Consultivo de Ciencias de la Presidencia de la República, que ese realmente no tiene mucha importancia, es un grupo de viejitos que a veces nada más van a refunfuñar. Pero los otros dos yo creo que son muy importantes, ¿no? Entonces, dada esa situación, nos hemos puesto a revisar la ley y vamos a proponer una nueva ley. Entonces, ese borrador de ley me tocó a mí escribirlo, ¿no? Y ya está en revisión con los secretarios, con la dirección general, y una vez que tengamos esta primera revisión, vamos a hacer un grupo de trabajo para poder revisarlo a nivel del CINVESTAB. Pero no tenemos mucho tiempo, así que tenemos que hacer esto rápido. Si ustedes ven la ley de ciencia y tecnología actual y la ley orgánica del CONACYT, ¿qué han logrado en todos estos años, ¿no? Han logrado tener una ciencia, yo diría, a buen nivel, ¿no? El CINVESTAB, por ejemplo, es el número 109 a nivel mundial de 8,000 centros. Somos el número 55 en América del Norte, que quiere decir Canadá, Estados Unidos y México. Y a nivel de Latinoamérica somos el número 3, ¿no? Tenemos ahí una institución de Brasil que está en el segundo lugar, perdón, en primer lugar, y luego en Argentina en el segundo lugar, y luego está el CINVESTAB. Pero de ahí los demás centros de investigación están muy lejos. El más cercano está en el lugar 950 y tantos, ¿no? Y luego los demás se van hasta el número 2000. Y aún cuando comparamos nosotros el CINVESTAB a nivel Estados Unidos, yo diría que lo que hemos logrado hacer es una ciencia de calidad, pero no es una ciencia Nobel, ¿no? Si nos comparamos con las universidades, Princeton, Stanford, Berkeley, Caltech, Penn State, estamos muy lejos, muy lejos. Probablemente uno de los problemas que hay que resolver, que se va a proponer, debería de corregir, yo creo que es la forma de calificar. O sea, la forma de calificar la investigación ha hecho que nos volvamos nada más productores de artículos, porque vamos a lo seguro, ¿no? O sea, vamos a no perder nuestra posición en el SNI, vamos a no perder nuestra posición, o vamos a posición para ganar un nivel dentro de la institución, y eso está sucediendo en todas las instituciones. Yo voy a calificar de esta manera a base de números, y no realmente crea nuevas teorías, crea nuevas ideas y va a buscarlas. Y puede ser que en el camino se equivoque y se tope con... Pero eso es bueno. Lo que es malo es que lo califiquen a uno mal por hacer eso. Y cuando logremos tener este tipo de calificaciones donde el esfuerzo, las ideas, las hipótesis, el trabajo matemático, físico, químico, biológico, hagamos de buena calidad, digan, sí, la persona hizo un trabajo de calidad, nada más que el camino que escogió no fue el adecuado, pero seguramente otros 2 intentos más va a llegar a donde quiere llegar. Y entonces íbamos a producir conocimiento de muy alta calidad, conocimiento que va a valer. Y yo creo que ahí es donde nosotros, y como comunidad, y más en este tipo de eventos como el que estamos ahorita, debemos de pensar. O sea, está bien producir conocimiento a la segura, pero también hay que producir conocimiento donde uno arriesgue a que las cosas seguramente nos permita corregir el siguiente paso y poder llegar bien a lo que sigue. O sea, un trabajo de ciencia en este sentido no toma a veces ni un año, ¿no? Nos puede llevar 4 años, nos puede llevar 10 años, nos puede llevar la vida entera. Pero seguro que si lo hacemos con calidad lo vamos a lograr. Y este es el mensaje que yo quería compartir con ustedes. Y ahora, si me permiten, pues vamos a inaugurar los trabajos de pie, que es la costumbre. Entonces, siendo las 11 de la mañana, declaramos inaugurados los trabajos de la 16ª conferencia tiene un nombre largo, ¿no? De Ingeniería Eléctrica, Computación, Ciencias de la Computación y Control Automático 2019. Espero que tomemos el conocimiento que aquí se va a compartir y que nos llevemos muchas nuevas ideas que podamos nosotros también para desarrollar nuestro trabajo. Y pues felicidades a todos ustedes.
Thank you all. All remaining to say is welcome to the conference. And I